Advanced Placement Chemistry, Hoover High School. This is your lesson for day 32. It's lesson 16, Gas Stoichiometry for Wednesday, October 14th. The due date officially is Friday, but go ahead and take till Monday to do this because we're getting this up late. So let's go ahead and get started. We're talking about gases. So gases have no fixed volume or shape. If you have a bottle of strong perfume and you open it up on a warm day, in about 15 minutes, you'll be able to smell the perfume throughout the room that you're in. So it went from having the shape and volume of the bottle to having the shape and volume of the room. And that's what's meant by gases have no fixed shape or fixed volume. So they can be thought of as atoms or molecules that have enough energy to break away from other atoms or molecules. And generally, but not always, gases are suspended. That is to say, they float in the atmosphere. So oftentimes, in other words, they can defy gravity. They have enough energy to move against the Earth's gravity. We'll deal with gas laws pretty much this week, but for now, all you need to know is the following important relationship for this lesson. At 0 degrees centigrade, the freezing point of water, and 1 atmosphere, that's the air pressure here in San Diego, 1 mole of any gas occupies a volume of 22.4 liters at STP, and that's the definition of STP, 0 degrees centigrade and 1 atmosphere. So 1 mole of any gas equals 22.4 liters. So that is called STP. Now, 0 degrees centigrade might seem kind of cold, freezing point of water, but for gases such as O2 or H2 or helium, that's not very cold. It takes hundreds of degrees below zero to get them to freeze, to collect together as a liquid, or even to become a solid. So 0 degrees centigrade is not cold for a typical gas. All right, so we're going to use the same kind of graphic organizer that we used before. This one's a little bit simpler though, because you need to, first of all, you need to be in moles to be in a chemical equation. Chemical equations count 2 hydrogens, this one for every oxygen, 2 hydrogens for every oxygen. It's a molecule, it's an atom or molecule counter. And so it's counting atoms and molecules. It doesn't understand grams or liters or anything else. So if you have liters of gas out here in our world that you measured in some container, you have to make that standard conversion of 1 mole equals 22.4 H2 hydrogen in order to get inside the chemical equation where you can find the relationships between those elements or compounds. So let's go ahead and just work a quick sample problem here. So how many moles of O2 gas is in 44.8 liters? So for this one, you don't really need the chemical equation. You have 44.8 liters. You have 1 mole for every 22.4 liters. So liters of O2 cancels with liters of O2. And you have 44.8 times 1 divided by 22.4 gives you 2 moles of oxygen gas. Okay. Now, how many moles of H2O gas, water vapor, in 44.8 liters? So again, 44.8 liters of water, 1 mole for every 22.4 liters. Liters of H2O cancels with liters of H2O. And again, you end up with 2 moles. So the point being of that exercise is it doesn't matter what the gas is. As long as you know what volume you have, 22.4 liters at standard temperature pressure, that's key, then you'll know how many moles you have. So these examples show that the relationship of liters to moles of gas does not depend on the kind of gas. Now what we can do is take that graphic organizer on the previous page and combine it with the one that we used for stoichiometry last week. So what we have down here, if you look at the bottom half of this, it looks exactly like the one we did last week. And for this particular reaction, you would have the molar mass of hydrogen, 1 mole of H2 equals 2.02 grams. For oxygen, it would be 1 mole equals 32. Remember, it's not the mass of just a single oxygen atom, it's the mass of an oxygen molecule. And for water, it's 1 mole equals 18.02 grams. You've seen that number a lot of times. That's to get from grams into moles. Inside this dashed line, that's chemical world, you have to be in moles. We can then go ahead and put the liters up on the top here, and it's that standard relationship we just mentioned, 1 mole for 22.4 liters. So now what we have is a situation where we can either start with grams or liters and end up with either grams or liters, just by the path that we follow. All right, so let's go ahead and take an example problem here. how many grams of H2O can be formed from 11.2 liters of H2 gas? So for grams of H2O, and if you're going to use this graphic organizer right lightly, you're going to have grams of H2O. It's right here. It's down here in the grams row, and it's under H2O. And then it says it's formed from 11.2 liters of H2. So here's H2, and you're going up to liters up here. So this is 11.2. So now what is our path to get from what we know, 11.2 liters, down to some unknown number of grams? Well, it's a three-step conversion. We come into the equation using this conversion right here, liters to moles conversion. Then we go across the equation from H2 to O2 in moles. And then we come out of the equation so that we have grams of H2O. And that's demonstrated down here. It's already written out for you. So first you go from liters of H2 using this conversion. So there it is right there. You have to make liters of H2 cancel out. So you remember you can have two ratios, 1 mole of H2 over 22.4 liters or 22.4 liters over 1 mole. You have to put the one with liters of H2 on the bottom so that they cancel like that. And now you're sitting right here. Now you need to come across from 2 moles of H2 for every 2 moles of H2O. That's an easy 2-to-2 relationship. You need these moles of H2 on the top here to cancel because they don't appear in the final answer. So you have 2 moles of H2O on the top, 2 moles of H2 on the bottom. So moles of H2 cancels with moles of H2. Now you're sitting in this box right here, moles of H2O. And you need to come out using the molar mass conversion for water to get to grams. So you have moles of H2 here, you need moles of H2 here on the bottom to cancel. And the last man standing is the grams of H2O. And there it is right there. So now you have your numbers set up, 11.2 times 1 times 2 times 18.02 divided by 22.4 divided by 2 divided by 1, and that gives you 9.01 grams of H2O. Okay, so it's very similar to the last time. When we did a 3-step before, we started with grams and ended up with grams somewhere down here. So it was up, over, down. Now it can be up, over, down. We can still do that, or it could be from the top. You can come in with liters, come down, or you could come in with grams and come out into liters, assuming that you're dealing with a gas as your product. Okay, one more example. So how many liters of H2O can be formed from 2.4 grams of O2? So we'll come back here. Let's erase these. Okay, and it's how many liters of H2O? So we need H2O, we need to be up in liters, so here's the question mark up here, that's what we're trying to find, can be formed from 2.4 grams of O2. So here's O2, we got to come down to grams, there's the 2.4. Okay, so you go up into the equation using the molar mass of oxygen, of an oxygen molecule. Then you come across oxygen to water, that conversion, moles to moles right there. And then you come out of the equation using the standard gas moles to liters conversion right there to get to the question mark. Okay, so if you see that down here, so 2.4 grams of oxygen right there. Use this molar mass conversion. You need grams of oxygen to cancel out, so it's on the bottom. Cancels with that. Now you have moles of O2. That means you're sitting right here in the moles of O2 box. Now you got to convert between moles of O2, moles of H2O. There it is right there. 2 moles of H2O over 1 mole of O2. You have to pick the ratio that makes moles of O2 cancel out. Right there. And now finally you're going to go up. It's a little bit off screen, but you're going to go up. You're going to use the moles to liters conversion. That's true of any gas. And that's 22.4 liters of H2O for every 1 mole of H2O. So moles of H2O are canceling on top, bottom. Your final answer is in liters of H2O. And you can just run the numbers 2.4 times 1 times 2 times 22.4 divided by 32 divided by 1 divided by 1. And that'll give you 3.36 liters of H2O. So these are fairly similar to what we did last week. You just now have an added possible reactant or product in the form of liters of gas. All right, so in this one, I'm going to ask you to draw the graphic organizer yourself, okay? And I would like you to draw that as part of the assignment. If you're doing it on line paper, that's fine. If you're doing it here, you still have to draw it. So go ahead and pause the video and it'll take you a few minutes to do this. But again, what you want is grams on the bottom. You need the molar mass conversions next up. Then you need moles. You could actually put moles on either side, but I usually put it here. That's where we put it at first. And then up here, you're going to have liters. Okay? So go ahead and take a few minutes and draw that. Okay, so I finished drawing this. It doesn't have to be beautiful. Down here would be grams. This is the molar mass. That's the translator. Molar mass simply means mass in grams per mole. Up here is moles. That's inside a chemical world. If you want, you can draw your dashed line around this. So everything in there has to be in moles. This is your moles to liters conversion. And this is liters. Now, before we get started, you have to balance the equation. Always look at an equation and see whether it's balanced for you or not. When you got coefficients, it probably is. Let's just check it though. 3 carbons, 3 carbons. Hydrogen, it's 6 hydrogens, and 3 times 2 is 6 hydrogens. Oxygen, I have 1 there and 8 there. 4 times 2 is 8. That's 9 total. There I have 3 times 2 is 6, and 3 times 1 is 3 more. That's 9 total. So everything is in balance. All right, let's go ahead and work through these. So how many grams of... Okay, so how many grams of C3H6O are required to create 6.4 liters of CO2 gas at STP? So we want to know grams of this compound right here. So we come down grams, and it's asking how many. That's our question mark. Okay, are required to create 6.4 liters of CO2. So we come over to CO2. Liters of CO2 is up here, and we put a 6.4 there. So again, our equation is moving from left to right. It's moving from reactants to products. But our math equation is going to be moving from what we know to what we don't know. So how do we get there? All right, so what we do, the path is we come we start with the 6.4, what we know, and we come from 6.4 into the chemical world, into moles of CO2, then from moles of CO2 into moles of C3H6O, which by the way is called acetone, and then we come from moles of this compound out to grams using the molar mass conversion. Okay, so let's go ahead and set that up. What we know, 6.4. Okay, what we know to what we don't know, it's 3 conversions involved. So the first one is simply this one right here. Okay, and we have liters of CO2, that should be. We have liters of CO2, and that needs to cancel out. So we're going to have to put 1 mole of CO2 for every 22.4 liters of CO2. 22.4 liters CO2 is going to be on the bottom. Okay, so liters of CO2 cancels with liters of CO2. Good, so that puts us right here, okay? I'm going to draw this a little bit darker, this dashed line. So, you know, when you're in the chemical equation, it's right here. Okay, so now we're sitting right here. Now we have to go from moles of CO2 to moles of acetone. So it's 3 moles of CO2 for every 1 mole. Let's go ahead and write a coefficient there. For every 1 mole of acetone, or 1 mole of acetone over 3 moles of CO2. Which one do you want? Well, you need moles of CO2 to cancel out. So that's going to have to be on the bottom over here. So it's going to be 3 moles. 3 moles of CO2 for every 1 mole of acetone. Moles of CO2 here cancels with moles of CO2 here. And now at this point, we're sitting in this box right here. Now we need to come out using the molar mass conversion. We need moles of acetone to cancel out, and we need to end up with grams of acetone in our final answer. So we're going to use the molar mass conversion. The grams is going on the top. Moles of acetone cancels with moles of acetone. grams of acetone is the last man standing. So now it's 6.4 times 1 times 1 times 58.09 divided by 22.4 divided by 3. Okay, and I get 5.53. 5.532. We have only two significant figures here, so let's just leave it at 5.5. I won't mark you wrong if you put too many significant figures there. That's okay. All right, that's how we do that. You see, one thing I'm not doing anymore, I'm not writing out all the possible ratios and everything. I'm thinking that you can look at these now, see what your ratios are, what your two possible ratios are, and then choose the right one. All right, so we're going to compact that a little bit from what we've done in the past. Okay, next up. How many liters of O2 gas are required to produce 17.84 liters of H2O gas at STP? Okay, so let's go ahead and erase what we used in the last problem here. So liters of O2 gas is up here, and it's telling us, it's asking us for 17.84 liters of H2O gas. Okay, so what do you have to do? You have to use the moles to liters conversion to get in the equation. You have to move across using the relationship between moles of H2O and moles of O2, and then you come back out using the moles to liters conversion again. So let's go ahead and do that. So we're starting over here. I'll just write it silently. You go ahead and write it and see if you get what I get. Okay, so you have three conversions. You saw that. Liters into the equation, across the equation, back out to liters is three conversions. All right, so the first one is going to be moles of H2O for moles of H2O for liters of H2O. Liters has to cancel out, so okay. Next, we have to go across from. We're now in moles of H2O here. Liters of H2O canceled with liters of H2O. We're in moles of H2O. We've got to go to moles of O2. We need moles of H2O to cancel out, so the relationship is 3 moles of H2O for 4 moles of O2. We need moles of H2O to be on the bottom. Moles of H2O, moles of H2O. Okay, now we're over here sitting in this box, and we want to come back out to liters of O2 up here. So we need moles of O2 to cancel out. There's the conversion. So moles of O2, 1 mole of O2 is going to have to go on the bottom. Okay, so moles of O2 cancels moles of O2, and liters of O2 is what we want to finish up with. So now we can run the numbers. Now you see real quickly here, 22.4 is going to cancel with 22.4 there. That simplifies it. So 17.84 times 1 times 4, we cancel that, divided by 3, divided by 1. So go ahead and compute that, and I get 23.78. We can go to 3 significant figures because that is a measured value. You could measure it more precisely than 22.4, so we're only measuring it to 3 sig fig for the 22.4 liters. Again, the single digits, the number of moles is an exact number. It's saying exactly 3 moles, exactly 1 mole. It's not subject to significant figures limits. So I get 23.8. There's the answer. All right, keep going. We're going to be grinding these out for this week and next week and last week. So it's really important to get good at these stoichiometry problems. You're going to be doing them. They're really central to chemistry. So let's go ahead. How many liters of H2O can be produced from 2.25 grams of O2? So we're going to go from grams to liters. Let's come on up here. Erase what we did last time. And it wants to know how many liters of H2O. So here's H2O, here's liters, put a question mark up there. Be produced by 2.25 grams of O2. Here's O2, and grams is down here. Okay, so I'm going to go, the path is I got to go through molar mass to get into moles. I got to go across moles to moles, and then I have to come back out through liters to get the final answer there. So go ahead, I'll set that up, you set that up, and I'll set it up quietly, and we'll see what we come out with here. Okay, so there we go. We got 3 conversions. So let's go ahead and get started. I'll try to keep both on the screen at the same time the best I can. Okay, so we're going from 2.25 into moles into the equation using the molar mass. We need grams of O2 to cancel out. It's 1 mole equals 32 grams. So we're going to put grams on the bottom. And that's per mole. Grams cancels grams, and now we're sitting in the moles of O2 box right there. We need to come across, so we saw this relationship before. There's 3 moles of H2O for every 4 moles of O2. We need moles of O2 to be on the bottom of that ratio because we need it to cancel with this right here, moles of O2. So it's going to be 3. There it is. We cancel moles of O2 with moles of O2. And now we have to come out of the equation from moles of H2O up above, slightly off screen, to liters of H2O. So we need moles of H2O to cancel out. So we know there's 22.4 liters of any gas, and this is H2O, over 1 mole of H2O. Moles H2O cancels. You're left there with your final units. So it's 25.25, 2.25 times 1 times 3 times 22.4 divided by 32 divided by 4 divided by 1, and that gives you 1.18, and we're good. There really should be 2 more sig figs on this 32 because that's what's on your periodic table. And we got 3 sig figs here, so we're going to go 1.18. And sig figs aren't that hard in most chemistry problems because it's usually multiplications and divisions. And all you do is look at what number has the least number of significant figures of the ones you're working with, except for the moles. Those are perfect numbers. Those are perfect units of 1. You don't count those. And that'll tell you what your sig figs are. Okay? All right. Couple more. And I think I'll wrap up this particular lesson. I don't want any particular video to go more than 30 minutes. So let's go ahead and finish this problem. We'll go on to the others on a different video. Okay, so how many grams of O2 are needed to completely react with 8.92 grams of acetone? So it's grams to grams. So that's what we did last week. So let's go ahead and do that this week. After a while, it's hard to get all your erasures done really cleanly, but that's okay. All right, so it's saying how many grams of O2. So here's O2. We're going to come down to grams. It's right there, question mark. Is needed to completely react with 8.92 grams of acetone. So there's grams of acetone right here, 8.92. So we're going to go into the equation using molar mass of acetone to get moles of acetone. From moles of acetone over to moles of oxygen, that's a 4 to 1 ratio for oxygen, and then back out using the molar mass of oxygen there. Okay, so let's go ahead, write that out, and then look and see what I did. Okay, so this is what I get. So let's come back up here, try to keep this on screen. I'll do the best I can. So we're going from here into moles using molar mass, 1 mole for every 58.09 grams. So right here, I need grams of acetone to cancel out. So that means I'm going to need that on the bottom. So it's 1 mole. And that's for every 58.09. Okay, grams of acetone cancels there and there. Now you have moles of acetone. So that means you're sitting in this box right here. We need to get over to moles of oxygen. So it's 4 moles of oxygen for every 1 mole of acetone, or 1 mole of acetone over every 4 moles of oxygen. Well, we need moles of acetone to cancel out. So we're going to use, so we're going to have 1 mole of acetone on the bottom, and we're going to have the 4 moles of oxygen on the top. All right, so moles of acetone cancel. Finally, we need to come out to get the grams of oxygen. So that's 1 mole is 32 grams of oxygen. We need moles of oxygen to cancel out and grams of oxygen to appear in the final answer. So moles of oxygen is going to be on the bottom, and 32 grams is going to be on the top. I'm adding the zeros because it's 16.00 on the periodic table. If we multiply that by 2, we have 4 significant figures there. Okay, and so moles of O2 cancels with moles of O2. Grams of O2 is the last man standing. So now you go ahead and calculate. That's going to be 8.92 times 1 times 4 times 32 divided by 58.09 divided by 1 divided by 1, and that gives me 0.291. And I have lowest numbers right there, 3 significant figures, so I'm going to go with that. It's actually 0.292 is what I would have. Leading zero is not significant. Okay, and that's what you get, 0.292. Let me write it a little bigger here, be sure you can see it. Okay, and that's grams of oxygen. Okay. All right, didn't leave us with a lot of space on this one. But let's go ahead. We can see we're going from grams, which is outside of the chemical equation, to liters, which is also outside, but on the other side, but it's also outside. So I'm going to write this without even looking at the graphic organizer. You start with 6.4. I think most of you or many of you can do this at this point. That's H2O. And it's going to be 3 conversions. You have to go in, across, and out again. And that's going to give us some number, how many grams of acetone. So grams of acetone. Okay, so that's what it looks like. So let's look at the graphic organizer. Okay, so we have 6.4 liters of H2O, so that means we start up here, 6.4. And we're trying to get to grams of acetone, so that's down here. Let me erase that from the last problem. And that's my question mark. It's your question mark. So we're trying to get from 6.4 to here, so you got to go into the equation, across the equation, moles to moles, and back out using molar mass. Okay, so the first conversion is going to be 1 mole is 22.4 liters of water, and we need to make liters of water cancel out, so the 22.4 liters is going to have to go on the bottom. Okay, liters H2O cancels. Now we have to go from moles to moles of water to moles of acetone. So the relationship here is 3 moles of water for every 1 mole of acetone. So it's 3 moles of water over 1 mole of acetone, or 1 mole of acetone over 3 moles of water. Which one do we need to cancel? And down here, we need the moles of water right here to cancel out. So we're going to put the 3 moles of water on the bottom and the 1 mole of acetone on the top. Moles of water cancels here and here. Finally, we have to come out of the equation from moles of acetone to grams of acetone using the molar mass for acetone. So we need moles to cancel out of acetone and grams of acetone to appear on the top. So that number was 58.09 per mole of acetone. And that's for every 1 mole of acetone. Okay, so moles of acetone cancels moles of acetone. Grams of acetone is what you have left. So you're ready to compute everything on top. 6.4 times 1 times 1 times 58.09 divided by 22.4 divided by 3 divided by 1, and that's going to equal 5.53. We only have 2 significant figures there, so we'll call that 5.5. Okay, and that takes care of the first problem. Again, as you get proficient at these, you'll get to where they go pretty quickly, okay? They're not always quick, but they're quicker. You see, we cut out a lot of writing that we did last week with all the different ratios that we could use. By now, hopefully you can see how those ratios set up as you go along. Okay, there's more problems to come. I'm going to put those on a different video. I'm going to go ahead and get this up for you since it's late, and I'll go ahead and continue to make the video and get that up right away.